Designing a caching system for an API that operates across multiple regions with high availability involves addressing several challenges: latency, consistency, fault tolerance, and scalability. Below is a structured outline of how to approach this problem in a technical interview setting like Lemon.io. 1. Understand the requirements. High availability. The system must be resilient and always accessible, even during regional outages. Multi-region. The API is served globally. Latency should be minimized for users in different geographic areas. Caching. Reduce API response time and back-end load. 2. Choose the right caching strategy. Layered caching. Edge, CDN, caching. Use services like Cloudflare, AWS CloudFront, or Akamai to cache static content close to users. Regional, distributed, cache. Deploy in-memory caches like Redis or Memcached in each region. Application-level caching. Implement local in-process caching, for example using LRU cache. 3. Cache invalidation strategy. Use TTL, time to live, for data expiration. Apply write-through or write-behind cache strategies. For strong consistency needs, consider a publish-subscribe model, for example, Redis pub/sub or AWS SNS, to invalidate/update caches across regions. 4. Data consistency trade-offs. Eventual consistency is often acceptable for high-availability systems. If strong consistency is needed, for example, for user authentication, use centralized coordination or consensus protocols, like Raft, Paxos, but this increases complexity and latency. 5. High-availability architecture. Multi-region deployments with failover using DNS routing, for example, AWS Route 53. Deploy Redis clusters in each region and possibly use Redis Enterprise or Global Data Store for Redis for replication. Use health checks and auto-healing infrastructure, for example, AWS Elasticsearch with replication groups. 6. Example tech stack. CDN, Cloudflare or AWS CloudFront. Regional cache, Redis, Elasticsearch, or Memcached in each region. Cache coordination, Redis streams, AWS SNS/SQS. Backend, Node.js/Nest.js, Python Flask, or Java Spring Boot. Monitoring, Prometheus plus Grafana, AWS CloudWatch. Infrastructure, AWS, multi-region, Kubernetes, EKS, Terraform for IAC. 7. Diagram, if asked you'd sketch. Global user requests hitting the CDN. CDN forwarding to nearest regional API gateway. Regional service querying local cache first, then DB if needed. Replication/notification system to keep caches in sync. Fallback logic for regional failure, for example, use nearest healthy region. 8. Common follow-up interview questions. How do you handle cache stampede? What happens if one region goes down? How do you balance performance versus consistency? Can you scale this system for millions of users? What if some data is sensitive and shouldn't be cached? 1. How do you handle cache stampede? Cache stampede occurs when many requests simultaneously miss the cache and hit the backend, often during cache expiry or cold start. Mitigation strategies. Mutex locking, request coalescing. When a cache miss occurs, only the first request is allowed to rebuild the cache, for example, using a lock or semaphore. Others wait or return stale data. Example, use Redis Sanks, set if not exists, to acquire a lock. Stale while revalidate. Serve stale data while refreshing the cache in the background asynchronously. Randomize TTLs. Avoid mass expiry by assigning slightly randomized TTLs, for example TTL equals 300 plus RAN 0,60, to reduce synchronized misses. Early recomputation. Pre-warming. For known hotkeys, refresh the cache before expiry. 2. What happens if one region goes down? A multi-region architecture should be designed to gracefully handle regional failures. Failover strategies. DNS-based failover. Use Route 53 or Cloudflare with health checks to redirect traffic to the nearest healthy region. Global Load Balancer. Use AWS Global Accelerator or Google Cloud Load Balancer to route traffic intelligently across regions. Data replication. Ensure your database and cache, for example, Redis, replicate asynchronously across regions. Use global services or cross-region replication to sync data. Graceful degradation. If a region fails, serve slightly stale or cached data from a backup region while notifying users. Circuit breakers and retries. Wrap regional service calls in circuit breakers to quickly detect failures and fallback. 3. How do you balance performance versus consistency? This is often a trade-off, especially in distributed systems. General approach. Read-heavy systems. Favor performance with eventual consistency, for example, TTL-based cache, async replication. Write heavy or critical systems. Prefer stronger consistency, possibly sacrificing performance, for example, avoid caching sensitive transactional data. Techniques. Data categorization. Cache only non-critical, read heavy data, for example, product catalogs, but avoid caching sensitive data, for example, user sessions, unless there's a strong invalidation mechanism. Write through cache, write to both cache and DB simultaneously for better consistency. Cache invalidation. Use event-driven architectures, for example, Redis pub/sub, Kafka, to push updates to distributed caches when data changes. Multi-tier caching. Use fast, possibly less consistent edge caching plus consistent but slower regional/store cache for fallback. Interview tip. State clearly, in real-world systems, we often lean toward eventual consistency where strict correctness isn't business critical, and we optimize performance. But for sensitive workflows like financial transactions, consistency wins over speed. Using a regional, distributed, cache with systems like Redis or Mumcached means deploying a cache instance in each geographical region where your application is running. This reduces latency and improves performance by keeping data closer to the user. Here's how to effectively use it. Steps to use regional, distributed, cache. 1. Choose a cache technology. Redis supports persistence, pub/sub, and more advanced data types. Mumcached, simpler, faster for basic key value storage. 2. Deploy caches in each region. If using cloud providers like AWS, GCP, or Azure. AWS, use Amazon ElastiCache in each region. GCP, use Memory Store for Redis in each region. Azure, use Azure Cache for Redis in each region. Set up application to use the nearest cache. Your application should detect or know its current region and connect to the local cache endpoint. For example, use environment variables like cache_endpoint equals Redis Europe.example.com. 4. Handle cache population. Write through, update cache on write to DB. Lazy loading. Fetch from DB on cache miss and update cache. Preload, optional. Preload frequently used data on startup pot 5. Data synchronization strategy. Optional if the same user might access different regions. Use event-based sync, for example, Redis streams or a message queue. Or use periodic cache invalidation and let each region reload data. 6. Monitoring and failover. Use monitoring tools to observe cache hit/miss rates. Implement fallback to DB if cache is unavailable. Application-level caching refers to storing frequently accessed data in the memory of your Node.js application itself, without external systems like Redis or Mumcached. This is fastest but not shared across servers. Each instance maintains its own local cache. Use case for application-level caching. Great for small-scale apps or microservices. Ideal for caching config, tokens, user sessions, or frequently read DB results. Works best in stateless or read-heavy apps. Common libraries for in-process caching in Node.js. Luru Cache, Node Cache, Quick Luru. Benefits. Fast. No network calls. Simple. Minimal setup. Efficient. For low memory or localized caching needs. Limitations. Not shared between app instances. Lost on restart/crash. Can use more RAM if not pruned correctly. Where is the cache stored? Just like Luru Cache, all data is stored in the process's memory, RAM not persisted to disk. Lost when app restarts. When to use Node Cache? Use it when you want easy TTL-based caching. Your app is single instance or doesn't need cross-instance cache sharing. You want synchronous API calls for simplicity. Avoid it if you need cache sharing across regions or servers. You want persistent or distributed caching. Use Redis or Mumcached instead. In regional, distributed, caching, the cache is not the same across all regions. Each region has its own cache instance. When you deploy your application in multiple regions, for example, US, Europe, Asia, and you deploy a Redis or Mumcached server in each region, the cache in US region contains only data used or populated in that region. The cache in Europe region is separate and contains different data. There's no automatic synchronization between them unless you explicitly build it. How to achieve multi-regional replicas in Kubernetes? By default, Kubernetes replicas are scoped to a single cluster, which usually runs in one region. To make your app multi-regional with replicas, you need to architect your deployment using multiple clusters, each in a different region. You cannot run multi-regional replicas in a single Kubernetes cluster because nodes are region-zoned. Latency and networking between regions aren't suitable for one cluster operation. Instead, use multi-cluster architecture. How to use CDN? To use a CDN on AWS, GCP, and Azure, you typically start by hosting your content, such as a web app, images, or videos, on an origin server like S3, Cloud Storage, or Blob Storage. Then, you configure the respective CDN service to cache and distribute that content globally. On AWS, the CDN service is Amazon CloudFront. You create a CloudFront distribution and set the origin to an S3 bucket, an Elastic Load Balancer, or even an EC2 instance. Once the distribution is deployed, CloudFront caches your content in edge locations around the world. You then access your content using the CloudFront domain name or a custom domain mapped via Route 53. On Google Cloud Platform, GCP, the CDN offering is Cloud CDN, which integrates with HTTP's load balancers. You first create a back-end service, like a cloud storage bucket or App Engine, and place it behind an external HTTP's load balancer. Then, you enable Cloud CDN on the back-end service. GCP automatically caches content at edge points of presence, and you use the load balancer's global IP or domain to serve content. On Azure, the CDN is called Azure CDN, and you can choose from providers like Microsoft, Akamai, or Verizon under the hood. To set it up, you create a CDN profile and then a CDN endpoint. You specify an origin, which can be a blob storage account, Azure App Service, or any external web server. Once the endpoint is active, content is cached at edge locations and served via a CDN URL or your own domain. How to use Route 53? Using AWS Route 53 and its equivalents in GCP, Cloud DNS, and Azure DNS, involves managing your domain's DNS records to route traffic to your services, such as websites, APIs, or applications, hosted on cloud infrastructure. On AWS, Route 53 is a scalable DNS and domain management service. To use it, you register or transfer your domain to Route 53 or update your domain registrar's name servers to point to Route 53. Then, you create a hosted zone and define DNS records, like AAA, CNAME, MX. For example, you might point www.example.com to a CloudFront distribution, an S3 static website, or an EC2 IP address. Route 53 also supports advanced routing policies like latency-based, geolocation, failover, and weighted routing to direct traffic intelligently. In GCP, the equivalent service is Cloud DNS. You create a managed zone and configure your domain registrar to use Google's name servers. You then add DNS records to the zone, pointing to IP addresses, load balancers, or other Google services like App Engine or Cloud Run. Cloud DNS supports standard record types, AAA, CNAME, etc., and integrates easily with Google load balancers. In Azure, the analogous service is Azure DNS. You create a DNS zone corresponding to your domain and get the Azure-provided name servers. You then update your domain registrar to use those name servers. Within the Azure DNS zone, you define the appropriate records to point to Azure resources like app services, VMIPs, or Traffic Manager endpoints. Azure DNS also integrates with Azure Traffic Manager to enable global traffic routing based on performance, geography, or priority. Where to store large video files? To store large video files in AWS, GCP, and Azure, you use their object storage services, which are designed for scalable, durable, and cost-effective storage of large, unstructured data like videos. In AWS, you use Amazon S3, Simple Storage Service. S3 supports virtually unlimited storage, and you can upload files via the AWS console, SDKs, or CLI. It supports features like multi-part upload for large files, lifecycle rules for archiving, for example, to Glacier, and integration with CloudFront for streaming or global delivery. In GCP, the equivalent is Google Cloud Storage. It also supports large file uploads, offers multiple storage classes, standard, nearline, cold line, and integrates well with services like Cloud CDN and Transcoder API for video processing and delivery. You can use usutil, client libraries, or the console to upload your videos. In Azure, you use Azure Blob Storage, specifically the block blob type, which is optimized for large media files. You can upload via the Azure Portal, Azure CLI, SDKs, or Oz Copy Tool. Azure Blob Storage supports tiered storage, hot, cool, archive, lifecycle policies, and integration with Azure CDN or media services for video streaming and processing. All three platforms offer access controls, signed URLs, encryption, and CDN integration to securely and efficiently serve large video content to users. How to implement payment module. Designing a payment module for an e-commerce website involves building a secure, user-friendly system that integrates with a payment gateway, like Stripe, PayPal, or Razorpay, validates transactions, and links to the checkout and order system. Below is a full-stack design for such a module. Architecture overview. Frontend calls Payment API, Node.js, Nest.js, which calls Payment Gateway, Stripe/PayPal, which stores data into database, MongoDB/PostgreSQL, order and inventory system. PCI-compliant data handling. PCI DSS, Payment Card Industry Data Security Standard, defines strict rules for how you handle credit card information. If you store, process, or transmit raw card data, like card numbers or CVV, you are fully responsible for PCI compliance, which is complex and expensive. Best practice: don't touch raw card data. Instead, delegate card handling to a PCI-compliant provider like Stripe, PayPal, Square, or Razorpay. These services provide pre-built secure forms, for example, Stripe Elements, PayPal Checkout collect and tokenize the card data in the browser. Ensure that you never touch or store sensitive card info. By doing this, your backend stays out of PCI scope, minimizing compliance risk. Tokenized transactions. Tokenization replaces sensitive data, like a credit card number, with a non-sensitive equivalent token that can be safely stored, cannot be reverse engineered, is only usable by the issuing payment provider. How it works: spot on. Frontend calls the gateway SDK, for example, Stripe Elements 2. Card info is sent directly to the gateway, not your server. 3. The gateway returns a token or payment method ID 4. Your app sends this token to your backend, which uses it to create a payment. Stores it, if needed, for recurring billing or refunds. What is Mamba? Mamba is a card processing and issuing core, typically used by fintech companies, digital banks, or startups building card programs. It's back-end infrastructure that enables you to issue, authorize, and manage card transactions in real time. Mamba is more about building your own financial product, including things like virtual and physical card issuing, real-time authorization and decisioning, custom rules, for example, transaction limits, merchant filtering integration with MasterCard or Visa rails, developer-first APIs. Mamba is often used as a core banking or card issuing engine, rather than a plug-and-play checkout tool like Stripe or PayPal. What is Paymentology? Paymentology is a global card issuer processor, typically used by banks and digital wallets. It's focused on cloud-native, high-volume card transaction processing and supports debit, credit, prepaid card issuing, transaction authorization, reconciliation and settlement, AML and fraud tools, data analytics around card usage. Paymentology is known for real-time processing at scale and partners with major banks and networks. PCI DSS, Payment Card Industry Data Security Standard. Compliance is categorized into 4 levels, based on the number of card transactions a business processes annually and its overall risk profile. These levels define the extent of the security and reporting requirements needed to remain compliant. Level 1 applies to organizations that process more than 6 million Visa or MasterCard transactions per year. It also includes any merchant that has experienced a data breach or is otherwise deemed high risk by the card brands. These organizations must undergo a full annual audit conducted by a qualified security assessor, QSA, along with regular network vulnerability scans. Level 2 is for merchants that process between 1 million and 6 million card transactions per year. These businesses are typically required to complete a self-assessment questionnaire, SAQ, annually and undergo regular network scans by an approved scanning vendor, ASV, although some acquirers may still require a QSA audit. Level 3 is designated for companies processing between 20,000 and 1 million e-commerce transactions annually. These merchants must also complete an SOC and conduct quarterly vulnerability scans. Level 4 is for smaller merchants processing fewer than 20,000 e-commerce transactions annually, or up to 1 million total transactions across all channels. They are generally required to complete an SOC and may be asked to do vulnerability scans depending on their acquiring bank's policy. Implementing a digital banking platform involves a complex, multi-layered architecture that combines security, compliance, scalability, and flexibility. At a high level, the architecture includes user-facing components, apps and web, core banking functions, accounting, payments, cards, third-party integrations, KYC, fraud detection, and secure infrastructure. Brick emoji, general architecture of a digital banking platform. At the top, you have the channel layer, which includes the mobile app, web app, and APIs. These communicate with the back-end application layer, which handles business logic such as account management, transaction processing, card controls, and customer onboarding. This layer communicates with the core banking layer, a specialized system, either built in-house or using platforms like Mambu, Thought Machine, or Temenos, responsible for real-time ledgering, customer account lifecycle, and regulatory compliance. The payment and card processing layer handles integrations with payment networks, for example, Visa, MasterCard, SEPA, SWIFT, UPI, and card processors, for example, Mamba, Paymentology, Marqeta. It ensures transactions are authorized, logged, and reconciled properly. Additionally, there is a risk and compliance layer that connects to KYC/AML providers, fraud engines, and transaction monitoring systems to ensure regulatory compliance and security. Data generated across the system is processed through a data and analytics layer, which supports dashboards, customer insights, and financial reporting. All of these layers run on a secure infrastructure layer, typically based on Kubernetes or serverless platforms, hosted in cloud environments like AWS, GCP, or Azure. Infrastructure includes API gateways, firewalls, logging systems, and vaults for storing secrets and encryption keys. For communication between services, most modern architectures use REST or gRPC APIs, often connected through a service mesh for observability and resilience. Microservices or modular monoliths are common in this space to support rapid development and deployment of new features like savings vaults, cashback, or investment integrations. gRPC, Google Remote Procedure Call, is a high-performance, open-source RPC framework that enables communication between services using protocol buffers, protobuf. It's designed for speed, efficiency, and type safety, making it ideal for microservices architectures, real-time systems, and inter-service communication in environments like digital banking, fintech, or cloud-native apps. Key concepts of gRPC. gRPC works by defining services and methods in a protofile using protobuf syntax. These files are then compiled into client and server code in your preferred language, Node.js, Go, Java, Python, etc. The client can then invoke methods on the server as if they were local functions, over HTTP/2.